Welcome. In this video, we will take a look at a few more examples with linear velocity and angular velocity and how we relate the two. Just to remind ourselves of the connection between linear and angular velocity, we know that the linear velocity v is equal to omega, which is the angular velocity times our radius. So we know that formula. So let's consider the mixing blade problem here. So we have a mixing blade on a food processor, extends out 3 inches from the center. If the blade is turning at 600 RPMs, or we could call that revolutions per minute, what is the linear velocity of the tip of the blade in feet per minute? So we're looking for linear velocity in feet per minute. Okay, so let's consider drawing a small picture here to represent what we're looking for. We'll have a kind of a circular figure, and we have a mixing blade coming out of the center of this food processor. And we know this blade is rotating around our circle. That blade, we are told, is 3 inches long. And we're traveling at 600 revolutions per minute. So one thing to consider here, revolutions per minute is not in our regular units for omega, but with a small change, we can get this into radians per minute, which is really helpful for converting between omega and our linear velocity v. So our omega here, which is our angular velocity, we can say this is going to be our 600 revolutions per 1 minute. If I go to consider one revolution, well, in terms of a circle, that would happen to be 2 pi radians. To go all the way around our circle is always 2 pi radians. And so we can convert this omega to radians per minute using this small conversion. So we can say equivalently, omega can be written as 1200 pi, and this is going to be radians per 1 minute. So here we have our omega, and I know my radius of my blade, or at least the food processor in general, is 3 inches. So let's consider now representing our velocity. V is going to be omega, 1200 pi radians per 1 minute. And for right now, we'll just multiply by our radius, which is 3 inches. And so we can say our linear speed, we can write as 3 times 1200 will be 3600 pi inches per minute. The only problem here is since we're doing inches per minute, we want to do a conversion to get into feet per minute. That's the final measurements that we want, is feet per minute. So if I do inches per minute, I could go and multiply this velocity. If I convert this, I'll use a different color, convert this to feet per minute, I know that 1 foot is 12 inches. And so to get rid of those inch markers and get to feet, we need to divide by 12. And so when we do this, we'll find that our velocity in feet per minute is just going to be 300 pi feet per minute. And we'll use this as our final result for this one. So again, watch out for those change in units. We want to make sure that we have the accurate units for either the linear speed or the angular speed. All right. Let's take a look at a second example here, and we'll keep working through. This second example says a phonograph record is turning at 45 RPMs, that's again revolutions per minute. If the distance from the center of the record to a point on the edge of the record is 3 inches, find the angular velocity and the linear velocity in feet per minute of the point. Okay, so this has kind of two components. We want to find angular velocity first, and then we can go out and solve for the linear velocity. So let's start with that angular velocity. We know this is going to be omega. And generally, when we think about angular velocity, we always want to treat it with radians per time measurement. And for this one, looks like we're going to be in minutes, so we'll keep in minutes. So we can start with 45 revolutions. And that will be revolutions per 1 minute. Multiply by 2 pi radians over 1 revolution. This will get us in radians per minute, which will be our angular velocity units. So we cancel our revolutions, multiply by 2 pi, we get 90 pi radians per minute. That would be our omega. The second calculation we need to do is our linear velocity. And so when we take this omega, remember that our velocity, linear velocity v, is going to be r times omega. And so our radius here, if I wanted to do this in feet per minute, in our last question, we also were converting for feet per minute. I'm going to try to convert this in just a little bit of a different way so we don't have to do any work on the back half of this problem. If we consider really the radius of the spinning record from the center to the outside, this is still 3 inches. This is similar to our last problem. Here's another way we could calculate this. 3 inches is the same thing as 1/4 of a foot. Remember that 3 inches out of a full foot is 12 inches. And so that would be just 1/4 for feet. So it's 1/4 of a foot. So I could just put 1/4 in for my radius. So this would be 1/4 of a foot. So to find v, we can just take our omega times 1/4. That's a foot. And so when we multiply through here, if we divide, we'll end up with 45 pi over 2 when we reduce this. And this will be in feet per minute. So usually we'll want to keep these results in terms of pi, and this looks like a great place to finish up that problem. So we have our angular velocity, omega, and our linear velocity, v. We'll finish up with one more problem. This says that a gasoline-driven lawnmower has a blade that extends out 1 foot from its center. The tip of the blade is traveling at the speed of sound, which is 1,100 feet per second. Through how many RPMs is the blade traveling? So really, RPMs is another way of talking about angular velocity. So really, we're talking about angular velocity in RPMs. So let's consider what we'll have here. We know we have a linear speed. The blade is traveling at the speed of sound with a 1 foot diameter, or a 1 foot radius. So if I consider a picture, the blade extending out is just 1 foot, and I'm going at a speed of linear speed of 1,100 feet per second. So if I start with that linear speed, I can then take a look at what RPMs I might be traveling. So let's kind of work this backwards. If I know that V is equal to omega times my radius, we know that V is 1,100 feet per second equals, my omega is what I'd like to solve for. The radius here is 1 foot. And so when I solve for omega, really what we'll have is, if I divide both sides by 1 foot, we'll have units canceling here. 1 foot divided by 1 foot. These units will cancel, and I'll be left with omega as my units of 1,100 radians per second. But we don't want this in radians per second. We'd like this in RPMs, or revolutions per second. So one way we can get back to revolutions is saying 1 revolution is equal to 2 pi radians. And so we'll take these calculations and divide there. One other thing we want is revolutions per minute. Notice the M there. And so we'll want to convert this to a time measurement of minutes as well. So this would be 30 seconds, or 60 seconds, excuse me, seconds in 1 minute. And so this will end up giving us the units that we desire. So the radians cancel, and our seconds will cancel. We'll be left with revolutions per minute, which is exactly what we need. Do a little bit of cancellation here, and we'll kind of try to keep this in pi. 2 and 60 we can cancel out as 30. And when we calculate this omega, we'll have 33,000, looks like. We'll have 3 zeros across the numerator, 33,000 divided by pi. Pi is the only unit left there, all these left, and our revolutions per minute. Is left as our units. So we'll have 33,000 divided by pi. If you put this in your calculator, this will be approximately 10,504 RPMs, if you get that calculator out. So this brings our linear velocity all the way back to revolutions per minute if we're called to do that. So Thanks for watching this video. Feel free to go back to any part and watch it again. Thanks for watching the video, and I'll see you guys in the next chapter.